universe is a four-dimensional hypersurface in which move about all objects. This is space-time. Space-time is not entirely rigid. It possesses a certain geometry that might be distorted in the presence of mass and energy. It can bend. It is this curvature which is responsible for gravitation. A black hole is an object whose mass is concentrated in a single point, which we call the singularity. Because of their mass, black holes distort space-time around them. Very close to the black hole, space-time becomes so distorted that all objects and even light can no longer escape. This is the horizon of the black hole, a sphere inside which the curvature of space-time is so great that it becomes impossible to escape it. To better visualize a black hole, we can represent its geometry by doing what is called an embedding in mathematics. The embedding will give us a geometric shape, which faithfully renders how space is curved around the black hole. After the maths, we see that space around a black hole behaves essentially like a funnel. At a distance, it is rather flat, its bend is almost non-existent. However, the closer we get to the horizon of the black hole, the greater the gravitational pull. Surprisingly, at first glance, we have the impression that the very structure of the universe contains a hole. The existence of this hole might seem strange. We might wonder what would happen if a spaceship arrived at its edge. Does the universe stop at this hole? To answer this question, it is necessary to understand a certain mathematical subtlety. Our universe possesses 4 dimensions, 3 dimensions of space and 1 dimension of time. By representing the geometry of space, we overlook 2 of these dimensions. On one part, the horizon of the black hole is supposed to be a sphere, but here, to be able to represent space-time, we have cancelled out one of the dimensions of space. The horizon comes to be a circle. Furthermore, we have only represented the curvature of space, not that of time. We have deliberately overlooked the temporal dimension of our diagram. Consequently, the diagram is static. It represents the curvature of space at one unique moment in time. When it falls towards the black hole, our spaceship moves forward in time. Indeed, if time did not flow, then the spaceship would remain motionless. As such, when we look at the descent of the spaceship as time progresses, it is necessary for our embedding to evolve as well, such that it remains representative of the curvature of spacetime at each instant. When we make our diagram evolve in this way, we realize that the hole closes in on itself very quickly. Once it reaches the horizon of the black hole, the spaceship keeps traveling through it and continues its descent towards the central singularity. Mathematically, we can show that regardless of the observer, and even for a ray of light, this kind of hole in the universe will always close in on itself sufficiently fast for it to be unreachable. According to general relativity, the structure of space can allow for such a hole, but this hole must ultimately close in on itself extremely quickly, such that it is impossible to reach it. As such, the universe does not really possess any holes. But from the point of view of our imagination, and from that of mathematical elegance, this is not very satisfactory. Even if it closes in on itself very quickly, the hole does seem to exist for a brief moment, which seems strange. We get the impression that there is something missing in our theory, that it does not perfectly describe the situation. With mathematics, it is possible to duplicate the geometry of space inside our equations, to make a copy of it, only in reverse. In this reversed version, the copy of the black hole behaves differently. Instead of not being able to escape from its inside, all objects are on the contrary destined to escape from it. This is what we call a white hole. Now that we find ourselves in possession of this copy of spacetime, we are able to stick it underneath our original hole. This mathematical move is admittedly artificial and cannot be readily backed up by any sort of physical observation. It is merely a mathematical extension, which is motivated by the symmetry of equations. we form a structure which is much more satisfactory, with the shape of a tube rather than the simple hole. It is this type of structure which we call a wormhole. If such a structure exists, then the wormhole must necessarily connect two portions of spacetime together. It might connect two independent universes together, but it is also likely that it might connect two different parts of one same universe. In this way, it would form a geometric shortcut between these two regions, which light and objects could use to travel quicker from one place to another. Giving free rein to our imaginations, we can quickly start to dream of a future in which spaceships might go through such shortcuts in spacetime to travel from galaxy to galaxy. However, this wormhole, which is made up of a black hole and a white hole, and which we also call the Einstein-Rosen bridge, cannot be crossed. As we have seen previously, its structure in the shape of a tube closes in on itself extremely quickly, thus strangling any object as it ventures inside. In this way, it is impossible to cross, and all that can be done is descend towards the singularity of the black hole. Fortunately for our curiosity, there exist other geometries for wormholes, which are mathematically valid under general relativity and whose properties are more advantageous. Firstly, if a black hole rotates on itself, or if it possesses an electric charge, then it might be possible to cross the wormhole associated to that black hole. In this case, the central singularity is not a fixed point, but a ring, which generates around it a new horizon, through which it might be possible to pass. Having said that, this wormhole would only be crossable in one direction. It would not be possible to travel the other way, through the white hole. Theoretical physicists have come up with more sophisticated geometries, with properties that are more interesting, and which go beyond black holes and white holes to allow for true travel through spacetime. These wormholes are purely mathematical and conceived to obey certain feasibility conditions. Firstly, we want our wormhole to be crossable both ways. Unlike the Einstein-Rosen bridge, it must be deprived of any sort of horizon, so as to make any point crossable one way or the other. Secondly, the wormhole has to be stable in time. Indeed, if it closes in on itself, or if it is unstable, it would be very risky to travel through it. Thirdly, to be able to cross it smoothly, the tube which makes up the wormhole has to be sufficiently wide, otherwise it would simply be impossible to fit in it. Fourthly, the time necessary to cross that wormhole must be reasonable, a few years for example. If the journey takes billions of years, the wormhole would be of no great use. Finally, the gravitational forces generated by its geometry must not be too strong, so that they do not damage or stretch the structure of the spaceship traveling through the wormhole. Mathematically, there exist such geometries which are accepted by the theory of general relativity. One of the easiest examples is the Morris-Thorne wormhole. The Morris-Thorne wormhole possesses a number of very interesting properties. It has no horizons, no singularities, and is perfectly stable in time. It will not close in on itself while an object goes through it. This type of wormhole is particularly interesting in that it is purely geometric, meaning that its structure does not enable it to generate a gravitational pull. As such, it is possible to stay motionless next to such a wormhole without it either pulling us in or repelling us. When we might try to cross it, our spaceship will move along a geodesic, a straight line within the bend of spacetime. The geodesic lines of the Morris-Thorne wormhole are particularly interesting. Certain trajectories will enter the wormhole, go around in circles inside it, but end up coming out of the tube from the same end they entered. To go through this wormhole, given that it does not generate a gravitational pull to draw things in, it is necessary to orient the spaceship precisely towards the center of the hole. At first glance, just like for a black hole, light rays are deviated by this geometry. The wormhole acts like a lens, which distorts the image of neighboring stars. But since light rays can also go through, we can also manage to observe an image of the entities on the other side of the wormhole, thus visualizing the part of the universe with which it links up. The Morris Thorne wormhole is particularly elegant and seems to meet all the necessary conditions for the possibility of intergalactic travel. However, it's not that straightforward. Its existence relies in fact on it being stable by placing around it a sphere of negative energy. This negative energy is necessary to counter the tension of space-time, which continually forces structures of this type to collapse on themselves, as we saw with the Einstein-Rosen bridge. Unfortunately, as per general relativity, we can show that such negative energy is mathematically impossible, which means that stable wormholes cannot exist. As disappointing as this may seem, wormholes are thus impossible from the perspective of general relativity, because their existence as stable structures depends on the presence of negative energy over a long period of time, which is mathematically impossible. This strong principle is called the topological censorship theorem. It tells us that any wormhole-like structure will censor itself automatically, or in other words, close in on itself for any observer attempting to reach it. But these definitive conclusions are only based on general relativity. However, we know very well that this theory is not perfect. It does not take into account certain quantum phenomena which occur at microscopic scales. At these scales, other theories come into play, such as quantum field theory. According to this theory, which describes particles at a quantum scale, vacuums possess a certain energy, which is constantly agitated by fluctuations. These fluctuations are known as virtual particles, and we can liken them to ordinary particles that would appear and disappear extremely quickly. All these virtual particles generate a type of residual pressure in space, which in certain configurations acts in identical manner to negative energy. This is known as the Casimir effect. As such, even though general relativity seems to reject the possibility of stable wormholes, quantum phenomena could bring a solution to the problem. Certain scientists already imagine parallels between wormholes and the phenomenon of quantum entanglement. Moreover, certain more speculative theories, such as string theory for example, offer new perspectives to conceptualize the existence of natural wormholes, which would have formed just after the Big Bang, and which would have gotten stretched after their creation by the expansion of the universe. In string theory, such wormholes would be stabilized by cosmic strings, which are for now still purely hypothetical objects. Finally, if the existence of wormholes could truly be proven, it would bring about the question of time travel. Indeed, the theory of relativity, which works not on space but on space-time, does not prevent such an object from linking two different instants in time. We are still uncertain whether or not it would be possible to travel into the past, but wormholes could make it possible. Having said that, for coherence reasons, a wormhole would however never be able to take travelers further back in the past than the very moment of its creation. Wormholes are objects that are fascinating from a mathematical perspective. Studying them remains very speculative, but nonetheless enables us to reinforce our current theories by constantly putting them up to the test, and by constantly trying to push back their limits. Although the possibility of crossable wormholes should not be discarded entirely, as for today, the only people crossing wormholes are theoretical physicists, with equations as their spaceships.